Dalton's law of partial pressure states the sum of all pressures of all the different gases in a mixture equals the total pressure of the mixture. So P total is equal to the summation of all your partial pressures. Another way of looking at that, your total pressure is equal to your total number of moles times RT divided by V using the ideal gas law, which in essence means then you have your number of moles of A plus your number of moles of B plus your number of moles of B, number of moles of C, etc. All that time RT over V will give you my total pressure. But we can break that down a little further. We can say that the partial pressure, total pressure is equal to your number of moles of A times RT over V plus your number of moles of B times RT over V plus your number of moles of C RT over V, so on and so forth. Which in essence says that the total pressure then is equal to your partial pressure of A plus your partial pressure of B plus your partial pressure of C plus whatever, how many gases you have in your system. The composition of a gas mixture is often described in terms of its mole fraction. The mole fraction of a component gas is the fraction of moles of that component in the total moles of the gas mixture. Chi, meaning your mole fraction symbol, so the mole fraction of A is equal to the number of moles of A over your total moles. Note there's no units on mole fraction because your moles will cancel with your moles of your A versus your moles of your total moles. Mole fraction can also be calculated through partial pressure. We know that mole fraction is equal to number of moles over total moles. Well, if you solve for number of moles with PV equals nRT, you get P partial pressure of A, V over RT divided by the total pressure, V by RT. Well, you see that V over RT is going to cancel out, leaving the partial pressure of A over the total pressure. So mole fraction can be calculated by your moles, which makes sense, so natural. The number of moles of A over the total will give me my mole fraction, as well as taking the partial pressure of A divided by the total pressure will also give you the mole fraction of A. Rearranging chi equal to partial pressure of A over the total pressure. The partial pressure of the gas A is defined as your mole fraction times your total pressure. So the amount of moles of the total moles times your total pressure tells you the partial pressure of A. Let's look at an example. I have a 10-liter flask containing 1.031 grams of oxygen and 0.572 grams of CO2 gas at 18 degrees C. What are the partial pressures of O2 and CO2? That's the first part of the question. Second, what is the total pressure? And third, what is the mole fraction of O2 in the mixture? Well, we know that each gas can be treated independently by using ideal gas law. So we can look at it in the oxygen case, say the partial pressure of oxygen times volume is equal to the number of moles of oxygen times RT. And we can look at the partial pressure of CO2 times volume equal to the number of moles of CO2, RT, and then rearrange these for solving for pressure, which would be the partial pressure of oxygen. So your partial pressure of oxygen is equal to your number of moles of oxygen, RT, divided by V. Notice that I have 1.031 grams of oxygen, but I have to convert that into moles, so I use molar mass to convert the oxygen, 32 grams oxygen for every 1 mole of oxygen. Then we have a R, which is 0.0821 liter atmospheres per mole Kelvin. And then we had to change the 18 degrees C into Kelvin, which is 291 Kelvin. Then divide by the volume, which is 10 liters. My units cancel, leaving me in atmospheres. Do the math, and I get 0.0770 atmospheres of oxygen. We'll do the exact same thing with carbon dioxide. So I have my 0.572 grams of CO2, molar mass of CO2, 44.01 grams of CO2 per mole of CO2, times my ideal gas constant, 0.0821 liter atmospheres per mole Kelvin, times my temperature, 18 degrees C converted into Kelvin, 291 Kelvin, divided by my volume, 10.0 liters. Units cancel, leaving me with just atmospheres, which is my unit on my numeric value. If I multiply it, is 0.0310 atmospheres of CO2. So that gives me the answer to number 1. Second one is, what is the total pressure? Well, total pressure is just a summation of all the partial pressures. So that would mean I take my partial pressure of oxygen plus my partial pressure of CO2, add those up, and I get 0.1080 atmospheres. That's my answer to the second question. Third question, what is the mole fraction of O2 in the mixture? Well, the mole fraction can be calculated in several ways. We could figure out the moles of O2 I have and figure out the moles of CO2, add up those moles, and put the amount of moles of O2 divided by the total and figure it out. That'd be more work. The way that we work this problem, the easiest way would be to go through partial pressure. We know that the mole fraction is equal to the number of moles of oxygen over total moles. We also know it's the partial pressure of oxygen over the total pressure. I have these numbers already, so we just plug those in. 0.0770 atmospheres over 0.1080 atmospheres. My atmospheres cancel, remembering that mole fraction is unitless. And I get 0.713. So 71.3% of the moles in this system are oxygen. Homework 46.